Hello everyone, welcome to the 12th tutorial class on digital communication. In the last class, we have discussed digital modulation technique and geometrical representation of signal, and from that how can we draw the signal space diagram. Moreover, we have also discussed about the amplitude shift keying modulation technique and how can we generate or demodulate ASK. All these techniques are elaborated in the earlier classes. Now, in this classes, in this class, we'll discuss another important digital modulation technique, that is frequency shift keying. Formally, it is known as the FSK. Apart from the corresponding waveform and its signal space diagram, we shall also discuss the different generation and the detection techniques for the FSK digital modulation technique. Now, coming to the definition of FSK. As the name suggests, frequency shift. That means for this particular digital modulation technique, the frequency of the carrier is shifted or varied according to the binary signal, which is nothing but a stream of 1 and 0. So, in case of FSK, phase and amplitude of the carrier remain unchanged, but frequency varied depending on the binary signal. Okay, and it is also known as the binary frequency shift keying or BFSK also. Okay, so conventionally, uh, if we use a digital signal, it consists of 2 bit, that means 1 or 0. So conventionally, for 1, the frequency of the carrier is shifted upwards. That means for 1, high frequency is used, whereas in case of 0, frequency is shifted downwards. That means low frequency carrier is used for modulation purpose. So here you can see that for 1, high frequency, and for 0, low frequency is used. That means frequency is shifted or frequency is varied depending on the value of input binary sequence. Okay, so you can see that this is input binary sequence. Normally, if we consider unipolar energy, then 1 is represented by 1 volt, or and 0 is represented by 0 volt. You can see that this is the input binary sequence. And as per the definition of the FSK, we have already known that uh, for 1, the frequency of the carrier is shifted upwards. Here you can see that the portion where the 1 belongs, in that region the frequency of the corresponding carrier is high, and here it is 0. That means here the frequency of the corresponding carrier is low. Here again the frequency of the carrier is high, and again in this region low, high, low, like this. Okay, so this is the FSK modulated output waveform, where we use or where frequency of the carrier is shifted depending on the binary bit 1 or 0. Fine. Now coming to the geometric representation of BFSK. So you can see that as for 1, we represent the signal by ST1, as it is as for 1, high frequency carrier is used, so we represent it by STH. So the for that region we have used a cos 2 pi FHT. Okay, so if we substitute by a in term of power, so it will become 2 ps. Okay, and cos 2 pi FHT, and if we substitute it in term of energy, so it will become root over EB into root over 2 by TB into cos 2 pi FC plus omega t. while omega is the frequency shift or deviation. That means, or if we consider the frequency of the original carrier is fc, that means when one is transmitted, in that scenario, the frequency of the carrier has been shifted to fc plus omega. That means high frequency. Okay, and similarly for 0, st0 will be a cos 2 pi flt, and it will be nothing but root over eb into 2 by tb cos 2 pi fc minus omega t. That means frequency has been shifted downwards and by the value omega. So you can call it omega as frequency shift or frequency deviation. Okay, as you can see that the total fsk consists of 1 and 0, and for both cases carrier has been used. Okay, for 1 high frequency, for 0 low frequency. So the equation, mathematical equation for bfsk can be written as like this: st1 plus st0, that is nothing but root over eb by eb into 2 by tb cos 2 pi fc plus omega, plus root over eb 2 by tb cos 2 pi fc minus omega t. Okay, so this is the mathematical expression for the bfsk digital modulation. Now for geometric representation purpose, we uh, substitute the first two equation like this: for 1, st1 can be given by root over eb into phi 1t, and for 0, st0 it equal to root over eb into phi 2t, where phi 1 and phi 2 can be given by root over 2 by tb cos 2 pi fht, and whereas phi 2 t equal to root over 2 by tb cos 2 pi flt, and phi 1t and phi 2t are the orthonormal signal. That means the angle between them is 90 degree, or they are perpendicular with each other. So this is the geometric representation. Now using these two equation, we can plot the signal space diagram. So this is the corresponding signal space diagram. You can see that this one is the first axis for phi 1t. This is the first real valued function, and this one is the phi 2t. Both are the orthonormal, that means the angle between them are 90 degree. And you can see that for 1, the corresponding energy is root over eb, and for 0, corresponding energy also root over eb, but it is also in with respect to phi 2t, whereas for 1 it is with respect to phi 1t. So in phi 1t, the first point for symbol 1, the corresponding point is at this point root over ev or root over ps into tb, and where there is this is for the corresponding 0. Sorry, this one is the this one become inversed, that means this one should be sht and this one would be slt. So you can you can see that this point is root over pstb, and this point is root over pstb. This axis is phi 1t and this one is axis is phi 2t, and in phi 2t the first point is at root over eb or root over pstb for 0, and along phi 1 axis, phi 1t axis, the point located at root over eb or root over ps into tb. So this is the for symbol 0, sorry, symbol 1, and this is for symbol 0. So SLT, this will be not SLT, this will be basically SHT, and this will be SLT. Okay, and this is the decision boundary. Okay, now the distance between mm, the symbol in signal space diagram actually denote the noise immunity or error probability. So you can see that here the distance between these 2 points will be d square equal to root over pstb plus root over pstb square. Okay, so db will be root over 2 into eb. Okay, but remember, or that for ASK, the distance between the for symbol 1 and symbol 0 is root over EB. But here in case of uh, FSK, BFSK, the corresponding distance is root 2 into root over EB. So obviously, the distance is larger than the larger for BFSK compared to the ASK. So obviously, BFSK is more noise immune compared to the ASK. Okay. So this is the basically geometric representation of BFSK, and from there we have drawn the corresponding signal space diagram. Okay. Now coming to the PhD of the BFSK power, if we draw the power spectral density of binary frequency shifting, So we can see that the spectrum of the original baseband signal has been shifted into the 2 point. First one is the FH and second one is the FL, and that such that the distance between them is 2 FB. That means if we substitute them FH minus FL, so you can see that the distance from FC to FH is 2 FB, and distance from FL to FC is also FB. So obviously FH minus FL equal to 2 FB, and you can see that bandwidth, that means where the maximum spectrum has been maximum power has been has lie, that is in between this region. Okay, so this is nothing but the 4 FB. Okay, so in case of 4 F, in case of ASK, the bandwidth was 2 FB, whereas in case of FSK, bandwidth for BFSK is 4 FB. So obviously bandwidth requirement for BFSK is very large compared to the ASK, which is one of the major disadvantage of BFSK. So this is the power spectral density for binary phase shift key, binary frequency shift key. Now coming to the next point, generation of BFSK. So this is the block diagram of generation of BFSK. Okay, so BFS generation of BFSK consists of uh, two level shifter, two product modulator, one adder, and an inverter. Okay, so uh, here you can see that the corresponding blocks are connected like this. So this is the BT, which is nothing but the input sequence. That means it consists of 1 and 0. It is basically unipolar energy. Okay, so where 1 is represented by 1 volt and 0 is represented by 0 volt. So coming to the first case, so BT, if we this input sequences is applied on a level shifter. So what is level shifter? Level shifter is nothing but an amplifier where um, some kind of gain or amplitude has been changed. Okay, so you can see that uh, if we observe the corresponding equation, like this equation, like root over EB into 2 by TB, or root over 2 PS. So this amount of gain is needed to be introduced here. So here BT is nothing but PHT. Okay, uh, and if we level shifter, that means PS into TS, this amount of signal has been introduced here. Okay, so amount of gain is introduced here. Next, this signal is going to a modulator, product modulator, where others input is 512, and value of 512 is root over 2 by TB into cos 2 pi FH into T. Okay, and so and the second section, the BT is passing through an inverter. So what will happen? And 1 will become 0 and 0 will become 1. Okay, so and it will become corresponding PLT. Again, if we move to the level shifter, some amount of gain has been introduced here, so that is PS into TB, so the multiplied by PLT. And if we it go to the second modulator, second product modulator or multiplier, and here others input are phi 2 T, that is root over 2 by TB cos 2 pi FLT, and corresponding generated output will go to the adder section, and ultimately if we add them, that will become BFSK. Okay, so this is the basically generation of BFSK. The now question arises, how BFSK has been generated. So sorry, suppose consider this block diagram has no this second section. So if we remove this second section, what will become the output? So for this case, if this portion is not present, so what will happen? So this is basically PHT and this will be level shifter, and if we multiply them, so ultimately the corresponding output will be a, nothing but ASK, where in case of ASK, uh, for 1 carrier will be present, and for 0 carrier, there will be no carrier. Okay, but here so what will happen? So here the output of the first product modulator will be ASK, but the corresponding carrier frequency is high frequency. Okay, now for second case, if you consider the second scenario, as it is passed through the an inverter, that means one is going to one is converted into the 0 and 0 is converted to the 1. So after that, if after the corresponding level shifter, and if we use the second product modulator, the corresponding output from the product modulator is also an ASK. But in this case, what will happen? For the binary sequence 0, there will be carrier with low frequency, and for 1, there will be no carrier frequency. Okay, so that is the necessity of an inverter, so that ultimately we get this both equation. So first, by using first product modulator, we generate this, and by using second product modulator, we generate this, and after that, if we add them, we ultimately get binary phase shift key, frequency shift key. Okay, so EB into 2 by TB, that is the basically so this amount of an phase shift sorry level shifter has been introduced, and after that, and this is basically the corresponding carrier for the first product modulator, and this one root over 2 by TB cos 2 by fc minus omega t, that is the for second product modulator. Okay, I think it is very clear to all of you. So like this we can generate binary frequency shift keying signal. Okay, so all these are written here. So here it is written as that if the BT is same as the PHT, where 1 is represented by 1 volt and 0 is represented by 0 volt. Now level shifter is used, which is nothing but an amplifier, and we get the corresponding output PS into TB into PHT. Now, if this signal is multiplied with the fast carrier signal, that is phi 1t, using product modulator 1, we shall get the SK type signal at the end of the fast product modulator, and where one of the input data there is high frequency carrier, but 0 there is no input data. Sorry, for 0 there is no carrier. But ultimately, if you observe the FSK symbol, so for 0 there should be a carrier signal, but which has low frequency. So for this case, we need to use second stage. That means next BT is passing through an inverter, where 1 is converted to the 0 and 0 is converted to the 1, and that will become PLT, and if it's become passing through the level shifter, it will become root over PSTB into PLT. And if we use the second product modulator or the multiplier, where the corresponding carrier frequency is root over 2 by TB into cos 2 pi FLT, using second product modulator, we shall get the another ASK signal. But this ASK signal has the different characteristic. So if we consider the corresponding input data, for input data there will be low carrier frequency, for input data 0 there will be low frequency, and for 1 there will be no carrier. Okay, so if you add them, ultimately you get the BFSK. I think the generation of the BFSK is clearer to you. Now coming to the detection of BFSK. So using so there are basically two types of detection technique, from where we can extract or you can reconstruct the original digital sequence from the BFSK signal. Okay, so first one is the coherent detection. So in case of coherent detection, we know that we have total process is synchronized. That means there's some the in the receiver section, the frequency of the corresponding carrier signal is known to us, and we can we can locally generated this carrier signal FH and FLT. So you can see that BFSK has been applied to one end of each of the two product modulator. This is product modulator 1 and this is the product modulator 2, and for each cases BFSK has been applied. For product modulator 1, the corresponding others input is cos 2 pi f ht, and for second product modulator the corresponding input is cos 2 pi flt. So this corresponding sinusoidal signal is locally generated, whose frequency is well known to us. That means for BFSK, what is the corresponding frequency deviation and what is the value of FC is all known to the corresponding receiver. Okay, now this corresponding multiplied output is applied to the integrator similar to the ASK. Now, what will happen in case of integrator? It will become, yeah, it will give an DC output voltage level. So for first integrator, the corresponding voltage level is L1, and for the second integrator, the corresponding voltage level, output voltage level is L2. How we get the corresponding DC voltage level, that is already discussed in the earlier classes, earlier class of for ASK detection, coherent detection of ASK. So you can consider that. Now after that, we these two voltage level L1 and L2 will go to a comparator for decision making. So if L1 greater than L2, then obviously symbol 1 will be considered, and else if L1 less than L2, then we will consider as the input as 0. So this is basically the coherent detection, where we use locally generated carriers, high frequency and low frequency carrier for the detection purpose. So that's why we call it coherent detection or synchronous detection. Okay. Now coming to the non-coherent detection. So here there is no locally generated carrier. So instead of it, we are using two bandpass filter, two envelope detector, and two sampler and comparator. So you can see that incoming FSK signal has been applied to bandpass filter, but first bandpass filter is tuned to the FH, and second bandpass filter is second bandpass filter is tuned to the FL, and their bandwidth is sufficiently high, so that all the spectrum can be all the base spectrum for the baseband signal can be passing through it. So for the first bandpass filter, the corresponding out is passing through the envelope detector. So as you already know, the envelope of corresponding signal containing the baseband signal. So envelope detector will detect the corresponding voltage level, or it will extract the corresponding baseband voltage level. So each filter is followed by an envelope detector that detects the baseband signal low frequency component, or that hides in the envelope of the modulated wave, and the resulting output of these two envelope detector will applied into a sampler where uh, sampler and output of the sampler will go to the comparator. Okay. Now again, if this voltage level is greater than this, then obviously 1 will be detected, and else 0 will be considered. Ultimately we get the demodulated signal or demodulated binary sequences. Okay. So this is the basically non-coherent detection. Why do we call it non-coherent? Because we don't use any kind of locally generated carrier at end of the receiver section. Okay. Just we have used two bandpass filter. So first bandpass filter will what will it pass? What will it pass? It will pass this region, this portion, and second bandpass filter will pass this, and after that, depending on the corresponding binary sequence, envelope detected and corresponding an envelope will be detected, and if we sample them and if we compare them, then ultimately we get the demodulated signal as output. Okay. So coming to the conclusion section, so in this class we have studied property of the BFSK signal. So what is the waveform, what is the power spectral density, and what is the signal space diagram, what is the noise unity, and after that we have also studied the different generation and detection technique. So detection technique basically consists of two types. First one is the coherent, and second is the non-coherent technique. Okay. So this one is the basically binary frequency shifting digital modulation technique, where frequency of the carrier is shifted depending on the input binary bit, that is 1 or 0. So for 1, frequency is shifted upwards, and for 0, frequency is shifted downwards. Okay. So these are the few references. Thank you. If you have any question, please post them.